I'm Dr. T and welcome to my office. So when talking about solutions, it's always useful to think about, well, what substances will make solutions with what other substances? And to do this, for two things, for one to dissolve into the other, or both to dissolve into each other, depending on, kind of how you've got the thing set up. Then really what we've got to think about is what's holding them together and then what forces are pulling them into a solution or allowing the solvent to break up the solute and incorporate it into the solution. So with the solvent and the solute, I'm just going to make the assumption, which is not entirely valid, but it's helpful for this concept, that the solvent is going to be a liquid and the solute is going to be a solid. Although I will comment a little bit on liquid solutes because those definitely do exist, as well as really any combination you would like, with a couple of exceptions. Okay, so when we have our solvent, typically speaking, our solvent is going to be a covalent compound. There are liquid ionic compounds, or I should say room temperature liquid ionic compounds, because most things will melt if you get them hot enough. I'm not really going to jump too deep into those, mostly because they are fairly rare. Definitely cool, definitely some interesting research into those, but most of the time you're going to be interacting with a covalent solvent. Now, with your covalent solvent, it's going to have a couple of choices of intermolecular forces. Really what we describe it as is a range between very polar and very nonpolar. If it's only able to do London dispersion forces, it's going to be very nonpolar. If it's going to be able to do lots of hydrogen bonding, it's going to be very polar. It's going to have positive and negative ends to it. Not full positive and negatives, these aren't ions, but a partial positive and a partial negative end that's going to have a pretty meaningful impact on what's going on. Now, if your polar solvent is trying to dissolve an ionic compound, then typically what it's going to do is it's going to start trying to interact with the lattice. Now, you've got your arrangement of cations and anions, and that really creates a lot of stability, what we refer to as lattice energy. So what that solvent's going to need to do, if it is going to dissolve that, is to be able to surround the cations and anions. It's going to take the negative ends of the molecule and surround that around the cations and the positive ends around the anions. And it's essentially going to create what's kind of like a pseudo-lattice. What we usually refer to, if we're talking about water, spheres of hydration. And then that, coupled with the fact that once something dissolves into a solvent, it's got a lot more different ways it can figure. It can be much more disordered. Entropy can increase, and things tend to like to go so that entropy increases. And thus that's going to lead to the ionic compound being dissolved. That is, if the lattice energy isn't too high. If the lattice energy for that particular ionic compound is too high, it is too stable, then it won't dissolve. And thus it will become insoluble. So when we want to look at solubility, what we're really looking at is this kind of relationship between the lattice energy of the ionic compound in its solid form and then the entropy that's able to obtain the disorder, as well as the kind of pseudo lattice that the solvent is going to make around the ions. Now, if you have a nonpolar solvent, then it's not really able to create this pseudo-lattice. It doesn't have the positive and negatives going on. So these are typically going to be very poor at dissolving ionic compounds because they can't create the pseudo-lattice, and thus even a modest lattice energy is going to overwhelm its ability to pull it apart, etc. So in that case, you're not going to get something that's soluble. Now, I should point out here, when I'm talking about soluble, it's not a binary thing. Sometimes you can get a little bit to dissolve. So it's kind of a continuum. We'll talk a little bit later about equilibrium constants, and for solubility, there is such a constant called KSB. Okay, so let's look at what if the solute is a molecular compound. So in that case, what it needs to do, the solvent needs to be able to overcome the intermolecular forces holding the molecular solid together. It's not going to be breaking the covalent bonds. Those very rarely will end up getting broken. Typically speaking, you're only going to be breaking intermolecular forces. So kind of the same deal going on over here, just you don't have the actual rigid lattice that the ionic compounds have. If your molecular solid is going to have polar molecules, then you need to be able to interact polar molecule to polar molecule. Otherwise, the intermolecular forces of the solid are going to overwhelm that. Now, if your molecular solid is nonpolar, so these got predominantly London dispersion forces, then if you come in with a polar molecule, it's going to try and be very orderly, and you run into this interesting penalty of entropy, where you can actually require more order of your solvent in order to dissolve your solute, and thus things don't work out particularly well. This leads us to the general rule of thumb that like dissolves like. Polar solvents work well with polar solutes or ionic compounds, whereas nonpolar solvents tend to work much better at dissolving nonpolar compounds. Now, there's a couple of interesting quirks. For starters, if you've got a pair of liquids, we usually don't say that this liquid dissolved in this other liquid. The like dissolves like still applies, but typically speaking, we describe these in terms of miscibility. So if they mix, they're miscible. If they don't mix, literally oil and water, then they are immiscible. Now, the other scenario that gets a little bit interesting are those that are amphiphilic molecules. In this case, we have compounds that have a polar end on them and a non-polar end on them. So they're kind of like a polar molecule and a nonpolar molecule at the same time. The classic case here would be things like soaps and detergents. The two are slightly different, depends on exactly which atoms you have. For both of these compounds, you will have what's usually described as a polar head. This is an end of the compound that's very polar, will tend to interact with polar solvents like water, and things that interact with water we typically call hydrophilic. Hydro, water, phile, lover. So these are hydrophilic or hydrophiles. So we'll have a hydrophilic head, that's a polar head, and then it will have a nonpolar tail. These will typically interact with nonpolar solvents quite well, but not interact very well with polar solvents. In this case, when it's not going to be interacting with polar solvents such as water, we call this hydrophobic. Hydro, once again, water, phobic, fearing. And as such, you have a compound that can interact both with nonpolar substances, what we usually call greasy bits or greasy substances, as well as polar, and let's just be honest, most of the time we're talking water. And thus you get, a soap. What these will end up doing is once they go into a solution, they will stick the end that matches the solvent out, and the one that doesn't, they'll stick it in. So in water, they form these micelles with all the polar heads sticking out and the nonpolar tail sticking in. So yeah, that's a little bit about what dissolves with whom. So the take-home message here, like dissolves like, and with that, looking at polarity, you can usually get a solvent that will work for what you need. This is quite often, a thing that we chemists will do is start looking at solvents and picking solvents based on do they have a similar polarity to our solute, and that way we can get, our solution made. So with that said, have a wonderful day, and I'll see you in later videos.